Hello, I'm Leroy Chu, and I'm going to be talking about the equivalences of refutational QRAT. So this is a talk that will be given at the SAT conference in Lisbon this month. It's joint work with Judith Klimo. Broadly, the topics cover proof complexity, quantified Boolean formulas, and applications to satisfiability testing. Let me just begin. So first of all, I'm going to introduce quantified Boolean formulas. So QBFs are propositional formulas with quantifiers added to them, but these quantifiers only range over the values 0 and 1. So for example, we could take this propositional formula here and give it two quantifiers here, for all and exists, and this evaluates to true because for each x there is some y, there exists a y, such that y equals x, so it satisfies this thing here for every x. Quantifications are shorthands for connectives. So formally we define exists as a disjunction here and for all as a disjunction, as a conjunction here. So here's another example as well, exactly how that expands out. You could also, there's an alternative way of looking at the semantics of quantified Boolean formulas. So we can consider QBFs that are in closed premix form. That means that all the quantification is done on the outside, just as it is done here, and every variable is quantified. That's what it means to be closed premix. We consider those QBFs as a representation of a particular kind of two-player game. And this two-player game, we're going to label the players exists and for all. And the game is played by playing the prefix from left to right. Whoever's quantifier appears, they get to set that variable to a value. And the existential player is trying to make the propositional matrix become true under the assignment, and the universal player is trying to make this propositional matrix become false under the assignment. And who gets a winning strategy determines whether the QBF is actually true or false or not. So in particular, if a QBF is false, there exists a winning strategy for the universal player, which we'll be using a bit later. Okay. And here's just a very quick example. So we've got this exists E for all U, and then we've got two clauses here. It's in a conjunctive normal form. This QBF is false. Why is it false? Well, because there's a winning strategy for the universal player. No matter what the existential player plays for E, the universal player can win and falsifies a clause, falsifying the C and F, by setting U to the opposite value of E. Okay? So I'll move on. So QBF is a logic, and when we consider logics, we might naturally consider what proofs are. So I'm going to just talk a little bit about weak QBF proof systems, and then we're going to move on to stronger QBF proof systems like the aforementioned QRAT, which was in the title. So the weak systems, so for example, QResolution, QUresolution, which is an improvement of QResolution, and this calculus here, which is for all expansion plus resolution. Let's sort of think about various things that are going on in QBF. So we've got QBFs, and you might be interested in taking a QBF and finding whether it's true or false or not. That's QBF solving. QBF solving actually motivates these weak QBF proof systems. So these systems like QResolution, QUresolution, they're very close to these QCDCL solvers. And if you take an orthogonal approach known as expansion solving, then that's very similar to this calculus here. So if you look at a solver such as RARX, you can sort of capture what RARX is doing by what this proof system allows. Okay, so the idea here is that these proof systems are weak specifically because they're trying to capture what's going on in the solving. One of the properties that these QBF systems have, well, let's first look at the situation with QBF solvers. So if you're looking at a QBF, you might want to know what the winning strategies are once you found whether it's true or false. So if a QBF is false, you might want to know what is the winning strategy for the universal player that confirms this. And QBF solvers have the ability some of the time, to be able to extract the actual strategies out of the solving instances. So that's what I've just described here with this arrow there. And then we've had this relationship between QBF proofs and QBF solvers. And you can also do something very similar with QBF proofs. You have a QBF proof, and let's say that in theory there's some sort of algorithm that extracts in polynomial time some representation of this strategy. So normally the representation of this strategy that we use some sort of circuits, okay, some sort of Boolean circuits in order to represent these strategies. So for each variable there'll be a circuit given your opponent's moves. What do you do? Okay, so now let's move on to this stronger system known as QRAT. So QRAT is a universal checking format for QBFs. So it's not associated with any one type of QBF solver. What it's meant to do is it's meant to capture all possible solving inferences, including pre-processing. And we can ask this question about strategy extraction again for QRAT. So in this case, all three of these systems have this property where you can look at the proofs, and from that proof you can extract feasibly the circuits for the strategies. For true QBFs, we can actually take the QRAT system and extract the strategies. So we're going to focus on this question for false QBFs, because I think that's a harder question. So it might be that strategy extraction may not be possible if these proofs are too short and the strategies are too big. Okay, so for example, if QRAT really is that powerful, it might be able to prove something in a really short proof, but that particular QBF might not have short strategies. So any sort of strategy extraction fails if you just think of that logically in your complexity theory. Okay, so I can give another sort of example of what's going on here. So let's think of this chess metagame. So what is this metagame? Well, it's chess, but the first move that you do is actually to pick your color. So in this game, you get to pick white or black, and that determines whether you go first or second. In this sort of metagame, you're guaranteed a winner or a draw if you play optimally. Okay, and that is a statement that can be we could easily sort of mathematically prove that. However, when we come around to actually playing it, we still have, even though the proof is very easy, the strategy itself would be very hard. So this is not an example of an actual QBF, and it kind of breaks down if we went to complexity theory, because chess is just a game without parameters. So it's just, you just think of it as like being constant time or constant size. But like in general, just think of chess as being hard, and you can imagine this sort of phenomenon comes up when thinking about QBFs. This will come up later again. But now I want to talk about exactly what's going on with QRAT. So what is QRAT? What does it do? Why is it important? So QRAT, the motivation of QRAT comes behind what's done propositionally, and that starts with block clause addition. So let's imagine we have some C and F, and we have this clause C, and it has this, and that C has a particular literal L. Okay, if we have that C introduced into this C and F, and it turns out that C resolved in that L always produces a tautological clause. So i.e. for every D with not L in it, the resolvent with C, between C and D, always contains two complementary literals. Okay, then C is actually a useless clause in some sense, and it turns out its satisfiability equivalent to either add or remove it. Okay, so this is a condition. So this condition I've described here is about tautological clauses. So if your resolvent is always tautological, then you can add this. But that condition doesn't have to be so strong. As long as phi implies semantically the resolvent for every clause D with not L in it, C can be added or removed like a block clause. And this is where we're going to go along this RAT and eventually QRAT idea. So what we're going to do is we're going to look at an incomplete mode of inference known as unit propagation. So here, look here, I've used this semantically implies, and now I'm going to do something which is a condition which is sufficient for semantically implies, which is unit propagation. So a unit clause is a clause with only one literal. In unit propagation, what we have is if we have one of these clauses, we know that in a satisfying assignment, this thing has to be set according to that thing. So we set that assignment, simplify our CNF, and we might end up with more unit clauses. And this is where the propagation comes in. So we keep on doing that until we reach a fixed point, and we build up an assignment and simplify our CNF. If under our simplification we derive a clause C, this means that C can be derived from via unit propagation. This is a sound mode of inference. It's not complete, but it is sound. And likewise, we can think if we take the negation of C and treat it as an assignment, if we get the empty clause, then that's the same as this phi implying C semantically. Okay. And this is really quite useful, which this idea, which is known as reverse unit propagation, allows us to learn or infer a clause C with only some polynomial time checking. Okay? Right? All we have to do is we've got to guess a C, and then in polynomial time we can confirm it. Okay? And this is a very important part of the RAT and QRAT proof systems. Okay? So what we do is we combine block clause addition with reverse unit propagation in order to get a powerful proof system. So we could add a clause C to some CNF phi if under some particular literal L, this resolvent you have with all the possible D's with the negation of C in it is sort of like gives you an empty clause when you need to take the negation of it, right? So this is just what was happening here. We're just saying this thing is semantically applied, but the way that we're checking it is going to be via unit propagation, and we choose unit propagation because it's polynomial time. Okay, and we can use this as a universal. We can use this idea to build this DRAT system, which is used as a checking format for SAT solving. So that's its main practical use. This actually managed to get some media attention in some articles which were along the lines of world's largest proof. So this was this Pythagorean triples problem, which used the DRAT format to store, I think it was 200 terabytes of data to check this very, very exhaustive problem. On the theoretical side, what we know that DRAT is a strong system, and it simulates many of these known systems, and has been shown to be polynomial equivalent to extended Frege / extended resolution. So this is these systems, but you allow extension variables. You're allowed to add variables that define particular functions. Okay, and I just included this diagram here. Here's extended Frege. This is where the DRAT system is, and here we're talking about we've been talking about propositional proofs so far. We're going to be moving on to taking that to the QBF level next. Okay, exactly as I promised. So the quantified resolution asymmetric tautology. Okay, so this is taking this DRAT thing and making sure that it can be made sound and make sense in the QBF setting. So suppose we have a QBF. Suppose D is a clause with not L in it. Remember, this was important in DRAT. The outer clause of D with respect to L is the subset of D of all the elements left of L in the prefix, and we define that formally here. So this is anything left of L or equal to, and it is not going to equal L as well. Okay. And the condition that we're going to have is we're going to have some clause has this QRAT property with respect to some literal L in some CNF phi under some prefix pi if for every clause D with the negation of L in it, we get that C and not this outer clause implies the empty clause. Okay, so this is another sort of reverse unit propagation here, but for this resolvent here, this what is known in the literature as an outer resolvent, right? So in the QBF setting, we're going to have to, in some sense, we're not using all of D here. We're just using the outer clause of D. This is essential for it to be sound. Okay. And we can use that just as we did in DRAT to add new clauses, just as we did in block clause addition. So suppose C has QRAT with respect to some existential literal L, which is in C. We can add C as long as it has this particular QRAT condition. Okay, so after every clause, this outer clause here, if we add its negation to this thing here, we can get the empty clause. Okay, and this is a very powerful rule. In fact, it allows us to include variables in C that aren't already in pi. So this is why I've put pi dash here. I'm just going to sort of ignore that, I think, for the rest of the talk. But it does allow us to add these extra variables, which can get us to simulate extension variables in this way, which makes it very powerful, just as it did in the propositional setting. Okay, so why does this all work? Why does this QRAT rule work? Why do we have these conditions? Well, what we need to do to show that it works is show that it's a sound rule, okay? We're not going to show it's complete because there are actually other rules that are required for it to be complete. So just to show it's a sound rule. Okay, well, we need to show that if we add C and this is false, then it was already false, okay? This is what soundness is. So we can use the fact of the semantics of our two-player game. So the way that we show this first statement here is that we use the universal player's strategy that works for this in order to produce a strategy for the formula without C. Okay? So the universal player, let's assume, and we could assume inductively, so we'd start at the end and come first, that the universal player has strategy circuits for each of the universal variables y. And this is for this situation where we have C. We only need to change our strategy when our game under the winning strategy that we have falsifies C only. Okay? Because we're trying to show that this this thing here is false. We know that this thing is false under a certain strategy, but that strategy might only falsify C in the end. So that's when we would need to change things. Okay. So how do we do that? If the outer clause of some D is false, we don't need to change our strategy. Because if C is falsified, we get a contradiction somewhere else in phi, right? And this comes from our QRAT property. So this is essentially where our QRAT property works, right? If some outer clause is falsified, we know that this thing is false just by this unit propagation. It could be any semantic implication at this point. Okay, well, if C is satisfied by any literal, we actually don't need to change our strategy, right? Because if C is satisfied and under this strategy this thing is false, then something in phi has already been falsified. Okay, so what's the remaining condition? Well, it would be if all the outer clauses are satisfied, right? That's when we'd cause some issues, right? If all the outer clauses are satisfied, it could be that only C is falsified. So what we do in this situation is we observe that we can play as if L is true. Why is this the case? Well, the existential player has satisfied all of these outer clauses, right? All these outer clauses have been satisfied up to this point in the game before we set L. Now the existential player gets the choice of setting this L, right? And they don't really have any reason to set that L to false. Because if they set it to false, they're not going to satisfy any more clauses, right? All the clauses they could have satisfied have already been satisfied, so it's a useless gesture. So if they do set it to false, the universal player can just respond as if they've set it to true, right? And just continue along that strategy without any penalty, right? They're playing the harder game by doing that. And they know when they do that, they can still win, right? Because we know from case 2 that they have some way to win, right? Because in that case, when C is satisfied, they don't have to change. So I said that in strategy extraction, you want to output the circuits. So this actually gives us an inductive way to build up these circuits using QRAT-R. So we could take the circuit that was used when we have C, and we just move backwards building the circuit. And the structure that you build on it would be something that looks like this. And this is quite crude, but what you do is you have your strategy here, but you might change the input coming into where L goes, or the variable of L goes, depending on certain conditions involving the outer clause and whether C has been falsified yet. If that's the case, then what you can do is you can switch the value of L, changes your input, and you respond according to a different L input. This is exactly what we've described. Okay? So when I got the referee feedback on this, there was a few people who wanted the actual circuits here. So this is how you would actually construct the circuits. Okay, so I mentioned that QRAT addition is not really sufficient enough for this QRAT system to be complete. So there's actually many more rules. One really important rule that is in QRAT, but also in many QBF systems, is this universal reduction rule. What happens in this universal reduction rule is if you have a clause with some universal variable L in it, and this L appears rightmost of every other literal in this clause C, you're allowed to just drop that literal, right? And this makes sense in terms of what you'd be doing in this strategy, because if all the variables of C are already false, then that universal player is going to take the opportunity to falsify this clause, and thus falsifying the whole CNF. Always in that situation, it's beneficial to take that opportunity. And this can be expressed in a circuit, right? What happens here? Well, we're just doing the same thing as we did before. We're looking at what happens if you know that you've got a winning strategy here. Can you find a winning strategy here? Well, yes. You just have to make sure that your circuit that computes your value of L changes whenever C is false. Okay, it changes to refute the L here, so that's why it's got a polarity input. But QRAT doesn't just use universal reduction. It actually improves on it in a number of ways. The first way is via QRAT-U, which uses the QRAT property to calculate whether a particular kind of reduction is valid. The other way takes what we had before with universal reduction, but makes it even more general by adding a dependency scheme. Now, we didn't actually get too much progress with what's being done here yet. We are working on this, So we're just going to concentrate right now on this QRAT U. I haven't defined what this dependency scheme does, and I don't think I would have time anyway. Okay, so when QRAT U is a very similar circuit to circuit construction to what we did with universal reduction, right? We're going to be changing the polarity of L depending on not only the outer clause of C, but also these other outer clauses of the things that like block it. So these D clauses as well. If they're all satisfied and this outer clause of C is falsified, then it is safe to set this literal to false, is what we do. And we can combine this all together. So there are actually a few other QRAT rules, which I don't have time to mention. This is the ATA rule and the clause deletion rule. But constructing these circuits in reverse is actually fairly trivial. You can just take whatever circuit you've used before and just use it again. Because the inference is actually just propositional. It doesn't affect our game. However, with the method of with this extended universal reduction, we didn't have an obvious method of strategy extraction. We are working on that at the moment, so keep an eye out for that. But without that, we can't show a full strategy extraction for all these QRAT proofs. What we can do is we can say that any QRAT proof that only uses regular universal reduction and doesn't take advantage of this extended universal reduction actually has this strategy extraction property. And having this strategy extraction property gives it a number of proof complexity results, which I'll just go over here. So what we got was an equivalence with another system, which is extended QResolution. So extension is adding these extra variables, and I briefly mentioned that QResolution exists as a way to capture what's happening in QCD-CL solvers. But I've put an asterisk here for a reason, because we haven't quite got this, but we've got something very close and very promising. Let's define this notation here, f of np. So this is a proof system, f, augmented with a rule that we can derive any propositional implicant, right? So this is really useful when looking at QBF systems, right? We're looking at a QBF system, but we add this rule where we just do all the propositional implications. It means that when we analyze that proof system, we're not getting bogged down in what it does in its propositional inference, right? We're looking at the genuine QBF power of this proof system. And it turns out that this actually gives us an optimality result. If we take any QBF proof system that has polynomial time strategy extraction, we can simulate that system by this QBF system with this NP oracle, NP derivation rule, right? So these QBF proof systems, if you have an NP derivation rule, it's not technically a proof system anymore, right? It's because unless P equals NP, because proof systems have to be polynomial time checkable. But this is a really useful framework for studying QBFs, and as you can see, we can just say that a strategy extraction is equivalent to being simulated by this particular proof system. Well, it's not a proof system, but it's the same as being simulated by this proof system with an additional rule. And QRAT, excluding extended universal reduction and just using regular universal reduction, is simulated by the system because we know it has strategy extraction. If we get into the nitty-gritties of the proof of this theorem, then we actually find that it's a bit stronger. We don't need this NP oracle in its entirety. We only need to show that propositional extended resolution can succinctly prove certain tautologies, and that will show that these two systems are actually just equivalent. So what about the situation where we do have extended universal reduction? Well, we don't have a proof of strategy extraction yet, so we can't get this simulation result. And if we could, then we would actually show these that this thing is simulated by the system. So what's the situation there? Either it's going to have strategy extraction with EUR, or it's going to not have strategy extraction once we include EUR. And strategy extraction, well, I mean, it would be a shame if it doesn't have it, because it's often beneficial. Because sometimes we don't just want to know whether QBFs are true or false, we want to know how to play a game that might be associated with it. Because as I've described, QBFs model certain kinds of games, and if you want to study games, it might be an idea that you translate that into a QBF. So if you're studying chess instances, you turn that into a QBF, you put it in your solver, and you don't have strategy extraction, you're just told yes or no at the end, or white or black wins, or something along those lines, then that's kind of not always the point, because sometimes you actually want to know what that strategy actually is. What moves should you actually make? And at the same time, strategy extraction can also be harmful, right? So, because it means that certain obviously false QBFs conditionally become lower bounds for our particular kind of proof system. So, the example of this would be this family of false QBFs, right? So this family of false QBFs cannot have short proofs in a system with strategy extraction unless NP equals P space, right? So you've got for all Z if and only if some particular QBF which we're parameterizing by, then we can say that this thing is false. It's really easy to spot that, right? Because if we just expand this out, this is just saying that this QBF is both false and true, right? Which it can't be. But in order to calculate the strategy of that, we need to actually calculate which one it is. Is this QBF going to be true or false? And that in general, I haven't mentioned it yet, but solving QBFs in general is a p-space hard problem. So we cannot have short proofs in this system with strategy extraction unless NP equals p-space. Okay, so that's what I wanted to say about equivalence with extended Q resolution or extended QU resolution. I'll talk briefly about the other equivalence that we got, which was we showed that QRAT actually simulates a system that looked a bit stronger than it. So this is QRAT plus, and what it does is it adds this universal reduction rule that I described to unit propagation, because that's what's done commonly in QBF solving, right? You can understand this unit propagation in polynomial time, but any universal reduction steps that's something else that can also be studied in polynomial time. So that it just makes some sense that if you're doing that in solving, you should add that to this condition here. And it uses this thing here to find these asymmetric tautologies rather than using just unit propagation. You actually need some extra conditions to make sure that this is sound. So you make sure you're only reducing variables after this pivot variable L in the prefix. And what we did is we just showed that this QRAT plus is just QRAT, right? This extra conditions and stuff don't actually fundamentally change what this calculus does in a polynomial. There's a polynomial simulation between the two systems, is what I'm saying. There might be some practical reasons why you want to use QRAT plus though, rather than QRAT, especially if you're modeling solvers that are doing these sort of inferences. You might not want to use our simulation. Okay, so in summary, I've talked about equivalence of refutational QRAT. Which equivalences have I talked about? Well, QRAT and QRAT plus are equivalent systems, first of all. QRAT UR and QRAT plus UR are p-simulated by this Q resolution with this NP oracle. If extended Frege can prove certain propositional tautologies in short proofs, then refutational QRAT UR and refutational QRAT plus UR and extended QU resolution are all equivalent, right? And this might be worth pursuing by looking at what these propositional tautologies are in bounded arithmetic. So that will be one of the next projects that I'll be looking at. Also, we've got this hanging question of what happens with extended universal reduction, which we're trying to pursue. It's unknown whether extended universal reduction allows strategy extraction or allows this rule can be effectively simulated in extended QResolution with this NP oracle. Okay, thank you very much. Thank you for listening to my talk.